October 13th, 1942. Hucknall Aerodrome, Nottinghamshire, England. Captain Ronald Thomas Shepard, Rolls-Royce's chief test pilot, advances the throttle on a Mustang that looks nearly identical to the dozens already serving with RAF tactical reconnaissance squadrons. Same sleek fuselage, same low-drag laminar flow wings. But beneath the spinner, 4 aluminum blades catch the morning light where 3 had always turned before. The Merlin engine roars to life with a sound deeper and more powerful than any Allison-powered Mustang had ever produced. Shepard releases the brakes. The modified fighter, designated Mustang X, serial number AL975, accelerates down the grass strip with authority that surprises even an experienced test pilot. Where standard Mustangs typically needed 900 feet of runway to lift off, this aircraft breaks ground in less than 700. Climbing through 6,000 feet, Shepard pushes the aircraft higher, 10,000, 15,000. At 18,000 feet, the altitude where Allison-powered Mustangs began gasping for air and losing performance, this Merlin conversion continues climbing, as if the thin atmosphere means nothing. 21,000 feet. The airspeed indicator reads 425 miles per hour, more than 80 miles per hour faster than a standard Mustang could achieve at that altitude. The difference between the aircraft the RAF had been flying for months and the machine Shepard commands this October morning narrows down to 4 spinning blades, and the engineering insight that aviation experts across Britain had dismissed as unnecessarily complex. The 4-blade Hamilton Standard hydromatic propeller, the same design that American bomber crews depended on to survive missions over Europe, had just transformed the Mustang from a capable low-altitude fighter into an aircraft that could challenge the Luftwaffe at any height. Yet the story of how British and American engineers converged on this solution began 18 months earlier, when a single RAF squadron commander looked at performance test results and realized that the finest fighter airframe in Britain was being strangled by the wrong engine and the wrong propeller. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Wing Commander Ian Campbell Ord stood in the operations room at the Royal Air Force's Air Fighting Development Unit in April 1942, studying performance charts that documented a troubling pattern. The North American Mustang Mark I, powered by its Allison Pfiff 1710 engine, dominated every fighter in service below 15,000 feet. Above that altitude, the same aircraft that outran Messerschmitts at sea level became progressively weaker as air density decreased. At 25,000 feet, where Luftwaffe bombers cruised with impunity, the Mustang's single-stage supercharger delivered insufficient boost pressure to maintain combat power. German fighters attacking from altitude could dive through Mustang formations, knowing the British aircraft lacked the engine performance to pursue them upward. The tactical implications had forced Fighter Command to relegate the Mustang to Army cooperation duties, low-altitude reconnaissance and ground attack missions, where its speed and range remained valuable, but its full potential went unrealized. Campbell Ord recognized that the problem wasn't the airframe. North American Aviation's engineers had created one of the most aerodynamically efficient fighters ever built, using laminar flow wing sections developed in cooperation with the National Advisory Committee for Aeronautics. Wind tunnel tests at Langley had demonstrated that the Mustang's drag coefficient was lower than the Spitfires, lower than the Hurricanes, lower than any contemporary fighter design. That efficiency translated directly into speed and range that no other aircraft could match, assuming the engine could deliver adequate power. The solution existed less than 50 miles away at Rolls-Royce's facility in Derby, where the Merlin 61 engine was entering production for Spitfire Mark IX fighters. The 2-stage, 2-speed supercharged Merlin represented a quantum leap beyond the Allison's single-stage design, maintaining sea-level power output to altitudes exceeding 25,000 feet through precisely staged compression and intercooling. Campbell Ord invited Ronald Harker, Rolls-Royce's senior test pilot, to fly a Mustang and evaluate the airframe independent of its power plant limitations. Harker took AL968, a standard production Mustang Mark I, through a comprehensive flight evaluation on April 30, 1942. His report to Rolls-Royce management was unambiguous. The Mustang airframe was exceptional. Install a Merlin engine and the resulting fighter would outperform anything in RAF service. Rolls-Royce engineers, led by Chief Designer Reginald William Harvey Bailey, immediately recognized the potential. The Merlin 65, mechanically similar to the 61 but optimized for slightly lower altitudes, fit the Mustang's engine bay with minimal structural modifications. The increased weight, 355 pounds heavier than the Allison, required moving the wing forward by several inches to maintain proper center of gravity. More significant was the cooling challenge. The two-stage Merlin generated substantially more waste heat than the single-stage Allison, necessitating a larger radiator installation beneath the fuselage. But one critical component required complete redesign. The Allison-powered Mustang used a three-blade Curtiss electric propeller with a diameter of 10 feet 6 inches. That propeller, optimized for the Allison's power characteristics and rotational speed, was fundamentally inadequate for the Merlin's output. The new engine produced 1,450 horsepower at 19,800 feet, nearly 300 horsepower more than the Allison at altitude. Converting that power into thrust required a propeller system capable of absorbing the additional energy while maintaining efficiency across a broader altitude range. Hamilton Standard's four-blade hydromatic propeller, already proven on American heavy bombers and fighters, offered the solution. The design used engine oil pressure to move a piston connected through gears and counterweights to the blade pitch mechanism. A centrifugal governor automatically adjusted blade angle to maintain constant engine RPM regardless of airspeed or altitude, optimizing thrust throughout the flight envelope. Most importantly, the four-blade configuration distributed the power load across a larger total blade area, reducing the stress on individual blades while improving propeller efficiency. The British initially specified Rotol four-blade wooden propellers for the Mustang X conversions, using components already in production for Spitfire Mark IX fighters. These propellers, 11 feet 4 inches in diameter, were immediately available and required no importation from America. But Hamilton Standard's metal blades offered advantages that wooden construction could not match. Aluminum alloy propellers maintained dimensional stability across temperature extremes that caused wood to warp. They resisted moisture absorption that degraded wooden blades during prolonged operations. Most significantly, Hamilton Standard's hydromatic system provided feathering capability, allowing failed engine propellers to be rotated edgewise to airflow to minimize drag. In June 1942, Rolls-Royce began converting 5 Mustang Mark I airframes to accept Merlin 65 engines. The aircraft, designated Mustang X, carried RAF serial numbers AM203, AM208, AL963, AL975, and AM121. Each conversion presented unique engineering challenges as Rolls-Royce refined the installation through iterative testing. The first Mustang X, AL975, initially received a standard Spitfire Mark IX Rotol propeller. This four-blade wooden propeller, proven in service with Fighter Command, provided baseline performance data for comparison. The aircraft flew for the first time on October 13, 1942, with Captain Shepard at the controls. Performance exceeded every prediction. Top speed at 21,000 feet reached 425 miles per hour, more than 80 miles per hour faster than Allison-powered Mustangs at that altitude. The second conversion, AM208, incorporated refinements learned from the first flight test program. Engineers permanently sealed the front radiator flap, reducing drag and gaining 6 to 7 miles per hour additional speed. The same modification was subsequently applied to all test aircraft. This Mustang X achieved 433 miles per hour at 22,000 feet, establishing new performance benchmarks that convinced even skeptical RAF officials that the Merlin conversion was viable. The third conversion, AM203, received a specially designed Rotol four-blade wooden propeller 11 feet 4 inches in diameter, larger than the standard Spitfire propeller. This aircraft achieved 431 miles per hour at 21,000 feet, while demonstrating improved climb rate and ceiling. But wooden propellers, despite their immediate availability, presented maintenance challenges that concerned squadron engineering officers responsible for keeping fighters operational under field conditions. Hamilton Standard's metal 4-blade hydromatic propellers, 11 feet 2 inches in diameter, offered the performance and reliability that operational squadrons required. These propellers, designated model 6523-24, featured distinctive rubber cuffs at the blade roots that smoothed airflow into the spinner. Each blade was machined from a single aluminum alloy forging, heat-treated for strength, and carefully balanced to tolerances measured in thousandths of an inch. The hydromatic mechanism used engine oil pressure to rotate the blades through their pitch range, while the centrifugal governor maintained constant RPM automatically. The propeller system represented decades of development by Hamilton Standard's chief engineer, Frank Walker Caldwell. His variable pitch propeller design had won the Collier Trophy in 1933, aviation's most prestigious award, for demonstrating that automatic pitch control could dramatically improve aircraft performance. By 1942, virtually every American bomber and many fighters depended on Hamilton Standard hydromatic propellers to convert engine power into thrust efficiently. The question, confronting RAF officials in late 1942, was whether British industry could manufacture Hamilton Standard propellers under license or whether importation from America was necessary. Rolls-Royce favoured the Hamilton Standard design for its proven reliability and feathering capability. De Havilland Propellers, Britain's primary propeller manufacturer, argued that their wooden propeller designs were adequate and immediately available without the delays and foreign exchange costs of American imports. The debate was settled by combat necessity. By November 1942, the United States Army Air Forces had tested their own Merlin-powered Mustang conversion, designated XP-51B. American test pilot Bob Chilton flew the XP-51B for the first time on November 30, 1942, powered by a Packard V1650-3 engine, the American licensed version of the Merlin 68. The aircraft was equipped with a 4-blade Hamilton Standard, a hydromatic propeller from the start, and performance results were spectacular. Level speed of 441 miles per hour at 29,800 feet. Climb rate nearly double that of Allison-powered Mustangs. Service ceiling exceeding 38,000 feet. The USAAF immediately ordered 400 P-51B fighters in August 1942, gambling on performance predictions before any Merlin Mustang had flown. North American Aviation's Inglewood, California plant began tooling for P-51B production, while a second facility in Dallas, Texas prepared to manufacture identical aircraft designated P-51C. The critical path for both production lines involved Hamilton Standard's capacity to supply 4-blade hydromatic propellers in quantities sufficient to equip thousands of fighters. Hamilton Standard's East Hartford, Connecticut factory, already operating at maximum capacity, producing propellers for B-17 Flying Fortresses and B-24 Liberators, faced demands that exceeded available manufacturing capacity. Each 4-blade propeller required 47 precision-machined components, assembled by skilled craftsmen using specialized equipment. Wartime expansion had increased employment from 800 workers in 1932 to more than 20,000 by 1943. But demand continued surpassing output. The solution involved licensing Hamilton Standard's designs to refrigerator manufacturers and office equipment companies that possessed precision machining capabilities. Frigidaire, Nash Kelvinator, and Remington Rand established propeller production lines, converting peacetime assembly equipment to wartime manufacturing. These licensees eventually produced more than half of the 530,000 Hamilton Standard hydromatic propellers manufactured during the war, ensuring adequate supply for American and British aircraft. British orders for Merlin-powered Mustangs, designated Mustang Mark III in RAF service, specified Hamilton Standard 4-blade hydromatic propellers as standard equipment. De Havilland Propellers received manufacturing licenses and began producing propellers to Hamilton Standard specifications at facilities in Hatfield. The wooden propellers initially fitted to Mustang X test aircraft were recognized as interim solutions, adequate for development testing, but unsuitable for sustained combat operations, where reliability determined whether pilots returned from missions over occupied Europe. The first production P-51B flew on May 5, 1943. The first P-51C followed on August 5. Both aircraft featured four-blade Hamilton Standard hydromatic propellers as integral components of their design. The propellers, combined with Packard Merlin engines and North American's exceptional airframe, created a fighter that outperformed German and Japanese aircraft in virtually every category of combat or performance. But the propeller's contribution extended beyond raw speed. The automatic pitch control reduced pilot workload during critical phases of flight, allowing pilots to concentrate on tactics and gunnery rather than manual engine management. During takeoff, the hydromatic propeller automatically shifted to fine pitch, equivalent to low gear in an automobile transmission. This allowed the Merlin engine to spin at higher RPM while producing maximum thrust for acceleration and climb. As the aircraft gained altitude and airspeed, the governor smoothly transitioned to coarser pitch, optimizing efficiency for cruise flight. If the pilot dove to attack or evade, the propeller automatically increased pitch to prevent the engine from exceeding safe RPM limits. And if an engine failed completely, the feathering mechanism could rotate the dead propeller's blades parallel to the airflow, removing massive drag that might otherwise send a single-engine fighter into an uncontrollable descent. These capabilities, proven through Hamilton Standard's decade of development and testing, transformed the Mustang from a promising airframe into the most effective long-range escort fighter of World War II. Yet, even as production accelerated and squadrons began receiving Merlin-powered Mustangs in late 1943, skeptics questioned whether the four-blade propeller's complexity justified its performance advantages. Fixed-pitch propellers, after all, had no hydraulic systems to fail, no governors to malfunction, no moving parts beyond the blades themselves. The answer would emerge not from engineering laboratories, but from combat operations over occupied Europe, where American and British pilots discovered that survival often depended on the margins of performance that four spinning aluminum blades provided. Those margins, measured in seconds of climb time and miles per hour of speed, frequently determined whether fighters intercepted German bombers before they dropped their loads, or arrived too late to prevent destruction. In aerial combat, where altitude advantage often decided the outcome, the Mustang's ability to climb faster and higher than Messerschmitt's created tactical opportunities that German pilots found increasingly difficult to counter. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. December 20th, 1943. Debden Airfield, Essex, England. Major James Howard of the 354th Fighter Group walks the flight line inspecting his squadron's newly arrived P-51B Mustangs. These aircraft, fresh from North American Aviation's Inglewood plant, represent the first Merlin-powered fighters assigned to the 8th Air Force for bomber escort duties. Howard stops beneath the nose of his assigned aircraft, studying the four-blade Hamilton Standard propeller that distinguishes these Mustangs from the Allison-powered variants he had flown during training. The propeller blades, 11 feet 2 inches in diameter, feature distinctive rubber cuffs at their roots and carefully machined aluminum surfaces that reflect the weak December sunlight. Each blade is stamped with manufacturing data and serial numbers that trace back to East Hartford, Connecticut, where skilled machinists had shaped the forgings to tolerances measured in thousandths of an inch. The spinner, painted olive drab to match the fuselage, conceals the hydromatic mechanism that automatically adjusts blade pitch throughout the flight envelope. Howard's engineering officer, Captain Robert Johnson, explains the propeller system's operation, while mechanics conduct pre-flight inspections. Engine oil pressure, routed through passages in the propeller hub, acts on a piston connected to the blade pitch change mechanism. A centrifugal governor, mounted on the engine and no larger than a coffee tin, senses RPM changes and it automatically adjusts oil pressure to maintain the pilot's selected engine speed. If RPM rises during a dive, the propeller increases pitch to prevent overspeed damage. If RPM drops during climb, the pitch decreases to maintain power output. The system requires no pilot input beyond setting desired RPM with a single cockpit control. Unlike manually adjusted propellers that forced pilots to constantly manipulate pitch levers during combat, the Hamilton standard design freed pilots to concentrate on tactics, navigation, and gunnery. That reduction in workload, seemingly minor in peacetime flight testing, became critical during combat, when seconds of distraction could prove fatal. But Howard's primary interest focuses on performance data that intelligence officers had compiled from combat reports filed by RAF Mustang Mark III squadrons already operating over France. The numbers revealed advantages that exceeded anything American pilots had experienced in P-47 Thunderbolts or P-38 Lightnings. Maximum speed of 441 miles per hour at 29,000 feet. Service ceiling of 41,900 feet. Combat radius exceeding 650 miles with internal fuel. These figures suggested the Mustang could escort bombers to any target in Germany and return to England with fuel reserves for combat. The first operational test came 11 days later on January 1, 1944, when the 354th Fighter Group escorted B-17 Flying Fortresses attacking German airfields near Paris. Luftwaffe fighters, primarily Messerschmitt Bf-109 G6s and Focke-Wulf 190 A8s, rose to intercept the bomber formation at 24,000 feet. The ensuing engagement demonstrated performance characteristics that German pilots had not encountered from American fighters. Captain Charles Gumm, flying Mustang serial number 43-6313, engaged a Bf-109 that attempted to climb away from pursuing American fighters. The Messerschmitt, powered by a Daimler-Benz DB605 engine producing approximately 1,200 horsepower, had consistently outclimbed American fighters through most of 1943. But Gumm's Mustang, its four-blade propeller automatically adjusting pitch to maintain optimal thrust, matched the German fighter's climb rate through 28,000 feet and continued accelerating through 30,000. The Bf-109 pilot, unable to escape vertically, rolled into a diving turn, attempting to use the Messerschmitt's lighter weight and smaller turning radius. Gumm followed, his Mustang's propeller automatically increasing pitch during the dive to prevent engine overspeed while maintaining control effectiveness. At 460 miles per hour, indicated airspeed, speeds where manually adjusted propellers required constant pilot attention to prevent mechanical damage. The Hamilton standard system managed engine RPM automatically, while Gumm concentrated on gunnery. 3 bursts from the Mustang's 450 caliber machine guns struck the Bf-109's wing root and engine cowling. The German fighter rolled inverted and entered an uncontrolled spin, trailing smoke and glycol coolant. Gumm pulled out of his dive at 15,000 feet, his propeller smoothly transitioning to fine pitch as he climbed back to rejoin the bomber formation. The entire engagement, from initial contact to confirmed kill, lasted less than 4 minutes. The automatic propeller had allowed Gumm to devote his full attention to combat maneuvering rather than splitting focus between tactics and engine management. Similar engagements occurred throughout that first mission, as 354th Fighter Group pilots discovered their Mustangs possessed performance advantages over Luftwaffe fighters that intelligence reports had suggested. But combat experience now confirmed. Lieutenant Glenn Eagleston, attacking a formation of FTW-190 fighters positioning for bomber attacks, accelerated from cruise speed to maximum power in seconds as his propeller automatically adjusted to absorb the increased engine output. The Focke-Wulfs, cruising at approximately 360 miles per hour, could not match the Mustang's acceleration or top speed. Eagleston closed to firing range and destroyed 2 German fighters before the survivors scattered into cloud cover. The performance gap between Merlin Mustangs and German fighters reflected not just engine power, but the cumulative advantages of automatic propeller pitch control. The Bf-109 G6, powered by the DB605A engine producing 1,350 horsepower, used a VDM electrically controlled propeller that required manual pitch adjustment by the pilot. German pilots, trained to manage propeller pitch as a standard part of combat procedures, still faced increased workload during the precise moments when concentration on tactics mattered most. The Focke-Wulf 190, using a similar electrically controlled propeller system, suffered from the same limitation. German engineering had produced excellent propeller designs, but none offered the fully automatic pitch control that Hamilton Standard's hydromatic system provided. That difference, seemingly minor in specifications, translated to measurable advantages during combat. American pilots maintained focus on enemy aircraft while their propellers managed themselves. German pilots divided attention between combat and engine management, creating opportunities for American fighters to exploit. By February 1944, 8th Air Force Mustang squadrons were regularly escorting bomber formations deep into Germany. The missions revealed another critical advantage of four-blade propeller design. Hamilton Standard's engineers had calculated that distributing power across four blades rather than three reduced the stress on individual blades while improving propeller efficiency, particularly at high altitudes where air density decreased. The result was measurable improvements in thrust at altitudes above 25,000 feet, precisely where bomber escort missions occurred. Technical data compiled by North American Aviation and Hamilton Standard demonstrated the performance difference quantitatively. A P-51B, equipped with a hypothetical three-blade propeller of equal diameter, would produce approximately 8% less thrust at 28,000 feet compared to the standard four-blade installation. That 8% deficit translated directly to reduced climb rate, lower maximum speed, and decreased acceleration during combat maneuvers. In practical terms, a three-blade Mustang would require approximately 90 additional seconds to climb from 20,000 to 30,000 feet, time that could determine whether the fighter intercepted attacking German aircraft or arrived too late to prevent bomber losses. The four-blade configuration also improved takeoff performance, critical for operations from British airfields, where runway lengths were often limited. The increased blade area allowed the propeller to generate higher static thrust, reducing takeoff roll by approximately 15% compared to equivalent three-blade designs. Mustangs could operate from forward airfields closer to combat zones, extending effective combat radius while reducing fuel consumption during transit to operational areas. But the propeller's most consequential contribution involved feathering capability during engine failures. On March 6, 1944, Lieutenant Robert Johnson's Mustang suffered catastrophic engine failure over central Germany after flak fragments severed an oil line. The Packard Merlin, starved of lubrication, seized completely at 24,000 feet, 200 miles inside enemy territory. Johnson immediately activated the feathering mechanism, rotating the propeller blades parallel to airflow to minimize drag. Without feathering, the windmilling propeller would have created massive drag, equivalent to deploying a parachute at cruise speed. The Mustang would have descended rapidly, forcing Johnson to bail out over Germany, where capture was certain. With the propeller feathered, the sleek Mustang airframe could glide efficiently enough for Johnson to nurse the crippled fighter westward. He crossed into Allied-controlled airspace at 8,000 feet and crash-landed in a French farm field. The aircraft was destroyed, but Johnson walked away with minor injuries. The feathering system had saved both pilot and valuable intelligence about German air defenses he had observed during his desperate glide home. 8th Air Force records documented similar incidents throughout 1944 as Mustang pilots discovered their propellers, provided survivability advantages that extended beyond pure performance. Hamilton Standard's decade of development work, refining hydraulic systems and feathering mechanisms through exhaustive testing, paid dividends measured in pilots who returned from missions that should have been fatal. The strategic impact became apparent as bomber loss rates declined dramatically once Mustang escorts became standard. During raids without fighter escort in autumn 1943, 8th Air Force bomber formations suffered loss rates approaching 20%, unsustainable levels that threatened to eliminate strategic bombing as an effective weapon. With Mustang escorts flying the entire mission profile, loss rates dropped below 4% by summer 1944. The difference represented thousands of airmen who completed their tours and returned home rather than becoming casualties or prisoners. German response to the Mustang's performance advantages involved desperate attempts to field fighters capable of matching American capabilities. The Messerschmitt Bf 109K4, introduced in autumn 1944, featured the DB605D engine producing 1,850 horsepower, and driving an improved VDM propeller. This variant achieved maximum speeds exceeding 450 miles per hour at 20,000 feet, marginally faster than the P-51D that had begun replacing P-51B models in American squadrons. But the K-4 arrived too late, and in insufficient numbers to affect the air war's outcome. Only 700 were produced before Germany's collapse, compared to more than 8,000 P-51D Mustangs manufactured by North American Aviation. The production disparity reflected not just industrial capacity, but the accumulated advantages of established supply chains. Hamilton Standard and its licensees produced propellers faster than German manufacturers could deliver equivalent systems, ensuring American squadrons received aircraft while German units waited for equipment. The performance comparison between the P-51D Mustang and Bf-109 K4, when flown by equally skilled pilots, demonstrated the Mustang's advantages. Maximum speed favored the Mustang by approximately 15 miles per hour at 25,000 feet. Service ceiling advantage exceeded 5,000 feet, allowing American fighters to attack from positions where German aircraft struggled to respond. Combat radius was more than double, permitting Mustangs to engage anywhere over Germany, while Bf-109s faced fuel limitations that forced early disengagement. Most significantly, the automatic propeller pitch control continued, providing the workload reduction that gave American pilots tactical advantages during the critical seconds when combat maneuvers demanded full attention. German pilots, managing manual pitch controls even in the K4 variant, still faced the distraction that Hamilton Standard's engineers had eliminated from American operations. That persistent difference, seemingly minor in peacetime evaluation, proved decisive during combat, when fraction of a second delays in reaction time determined survival. Lieutenant Urban Drew, flying with the 361st Fighter Group, encountered 6 Bf-109 K4s, escorting Messerschmitt Me 262 jet fighters, near Berlin on October 7, 1944. The engagement illustrated how Mustang performance advantages translated to tactical superiority. Drew climbed to 32,000 feet, altitude where his Mustang maintained full combat power, while the Bf-109s struggled to generate adequate thrust from the thin air. Attacking from above with both altitude and speed advantage, Drew destroyed 2 Bf-109s in his initial pass before the survivors could react. The German fighters attempted to escape through diving turns, but Drew's Mustang, its propeller automatically managing pitch throughout the engagement, maintained pursuit through violent maneuvers that would have required constant propeller adjustment in manually controlled aircraft. Drew damaged a third Bf-109 before fuel constraints forced him to break off and return to England. The combat report Drew filed that evening documented performance characteristics that German pilots could not match. His Mustang had climbed to 32,000 feet in approximately 13 minutes from takeoff. The Bf-109 K4s, according to German performance data, required nearly 16 minutes to reach the same altitude. That 3-minute difference allowed Drew to position himself advantageously before the engagement began. Once combat started, the automatic propeller freed Drew to concentrate fully on gunnery and maneuver, rather than dividing attention between tactics and engine management. By March 1945, as Allied forces advanced across Germany, and the Luftwaffe faced fuel shortages that grounded most units, Mustang squadrons dominated German airspace with impunity. The 4-blade Hamilton Standard propellers that had seemed unnecessarily complex to skeptics in 1942 had proven themselves the most reliable propeller design in combat service. 8th Air Force maintenance records showed propeller-related failures occurred in less than 1% of missions, lower than engine failures, landing gear problems, or hydraulic malfunctions. The reliability reflected Hamilton Standard's obsessive attention to quality control and testing. Every propeller shipped to combat squadrons underwent inspection procedures that exceeded military specifications. Blades were X-rayed to detect internal flaws. Hydraulic systems were pressure tested to twice their operational limits. Governors were calibrated to maintain RPM within plus or minus 25 revolutions per minute under all flight conditions. Components that failed to meet standards were rejected and returned to manufacturing for analysis, ensuring defects were corrected before they reached operational units. Frank Caldwell, Hamilton Standard's chief engineer, personally approved changes to manufacturing procedures and test protocols throughout the war. His insistence on reliability over production speed occasionally created friction with military procurement officers demanding maximum output, but combat results validated his priorities. Pilots trusted their propellers to function correctly during the precise moments when malfunction would be fatal, and that trust was rarely misplaced. The final measure of the four-blade propeller's contribution appears in statistics compiled by the Army Air Forces in 1945. Approximately 15,600 P-51 Mustangs were manufactured during the war, each equipped with Hamilton Standard four-blade hydromatic propellers. These fighters destroyed more than 4,900 enemy aircraft in air-to-air combat, while suffering approximately 2,300 losses to all causes. The favorable exchange ratio reflected numerous factors, including pilot training, tactics, and numerical superiority. But performance advantages enabled by the propeller contributed measurably to outcomes. Strategic bombing surveys conducted after Germany's surrender documented that the Mustang's ability to escort bombers throughout their mission profiles was decisive in achieving air superiority. Without effective fighter opposition, German industrial production declined as Allied bombers struck targets with increasing accuracy and decreasing losses. The industrial capacity that produced Hamilton Standard propellers in quantities sufficient to equip thousands of fighters represented a manufacturing achievement that German industry could not replicate under wartime conditions. The legacy of the four-blade propeller development extended beyond World War II. Post-war fighter designs, including the P-51H model that represented the ultimate development of the Mustang airframe, used improved Hamilton Standard propellers with wider blades and refined aerodynamic profiles. Jet aircraft eventually eliminated propellers from frontline fighters, but the engineering principles refined during wartime production influenced turboprop designs that powered transport and maritime patrol aircraft for decades. Hamilton Standard continued manufacturing propellers for civilian and military aircraft long after piston fighters became obsolete. The company's hydromatic design, proven reliable through millions of flight hours during the war, became the foundation for turboprop propeller systems that powered aircraft like the Lockheed C-130 Hercules and Lockheed P-3 Orion. Modern propeller controls, using electronic sensors and computer processing, automated functions that Hamilton Standard's mechanical governors achieved through elegant precision engineering. The machinists and engineers who built propellers in East Hartford, Connecticut during the war years could not have known their work would influence aviation for generations. They understood only that pilots depended on their craftsmanship for survival, motivation enough to maintain standards that ensured reliability under conditions where failure meant death. The four spinning aluminum blades that distinguished Merlin Mustangs from their predecessors represented not just technical achievement, but the accumulated effort of thousands of workers who transformed engineering drawings into components that performed flawlessly when lives hung in the balance. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.